So welcome to office hours. So what can I do for you, Sean?
Can we just like go over reflexivity, symmetry, and transitivity?
Sure. So binary relations and their properties, right?
Right.
So binary relations actually on a particular set A and then properties. Okay. So we can only play these games of reflexivity, symmetry, and transitivity if the binary relation is on a set A. Can you see this okay?
Yeah.
Seems like there's a glare. Okay. So that a little bit. So can you give me the definition of a binary relation on a set A? Thinking I might even turn this light off. I don't know. Is that better? Is that a little better?
Yeah, that's fine.
Can you see it?
Yeah.
Oh,
The definition is given sets A and B, any subsets are subset A cross B is a binary relation from A to B.
that's right. That's good. That is the definition of a binary relation from A to B. Now, if A and B are the same set, then we get ourselves a binary relation on a set A. And the definition here is given a set A, any subset, curly R, of A cross A is a binary relation on A. So A and B are the same set if we're talking about a binary relation on A. Okay. So we have three properties if A and B are the same set. So properties of a binary relation on a set A. So both coordinates are coming from the same set A. So the first definition is reflexivity. Curly R is reflexive if for all elements, say little a, in the underlying set big A, little a comma little a is in curly R. In other words, every element of the set A has to be related to itself. So if we used the relational notation, it would look like this. For all elements little a in A, little a is related to little a. Okay? Now, for symmetry, we need two elements to play the game. Oops. So curly R is symmetric. Do you remember what symmetric means?
I think what it means that's it's like it has like one element goes to that element and that element goes back to that element.
That's right. That's right. So to write it in symbols for all elements little a and little b in set A, if we have AB is an element of curly R, then, just like you said, B comma A needs to be an element of curly R. All right. And so if
All
we're
right.
so if we want to use our relational notation for all elements little a and little b in A, if little a is R to little b, then little b is going to be R to little a. Good. So finally, R is transitive. Do you remember what that means?
Um, I don't really know how to explain that. Well, that one is kind of like more difficult to me.
Okay, so we need three elements.
Hmm.
So for all A, B, and C in set A, two things in the hypothesis. If AB is in curly R and BC is in curly R, then we need AC to be in curly R. So it's a little easier to write this with relational notation. It goes like this: for all A, B, and C in set A, if A is related to B and B is related to C, then in some sense we're crossing over on the B, and we need to get that A is related to C. All right. So our arrow diagrams can help us check these properties: reflexivity, symmetry, and transitivity. So let's look at an example. So let's use the set A that's got the elements, say little a, little b, little c, and little d in it. And let's let curly R be a binary relation on A, and curly R is going to be this binary relation. Little a is going to be related to little a is going to be related to little c, little b is going to be related to little b, little c is going to be related to a, c is going to be related to c, and d is going to be related to b. All right. So let's check reflexivity. In fact, let's draw the directed graph. That's A. Let's draw the directed graph. I keep calling them, accidentally calling it arrow diagram, but it's directed graph of curly R. All right. So we've got four elements in the set A. So we can just spread them out a little bit so we have room to make our arrows. So we've got little a, little b, little c, and little d. Okay. Then we make an edge from x to y if the ordered pair x comma y is in the relation. All right, so A is related to A. So we're going to put a loop from A back to A. A is related to C. So we're going to make an edge from A to C. B is related to itself, so we'll put a loop at B. C is related to A, so we'll put an edge from C back to A. C is related to C, and D is related to B. So when we're checking for reflexivity, what do you think we need to see in the directed graph? Let's check curly R for each of the three properties. So let's look at reflexivity. For this relation to be reflexive, which ordered pairs do we need to see in the relation? Or equivalently, what do we need to see in the graph?
That the elements go back to themselves.
That's right. Each element, for every element, little a in set A, that element has to be related to itself. So that means we need to see a loop at each vertex. Do we see a loop at each vertex?
No.
No, we don't. Hi, Isaiah. So talking about these properties of
Hey,
binary
Professor Good.
relations. Hi,
Sorry, I'm a little late. I just got home, but
don't worry. Don't worry
see you
about
guys
it.
going over reflexivity, and symmetry, and transitivity.
That's
Trans
right. So we're
I got you.
checking this relation for reflexivity, and we just realized, huh, it's
It's not
not.
reflective.
Go ahead.
I was gonna say it's not reflexive because there's a set with DB, but there's no set with DD, so it doesn't check the box for reflexivity.
That's right. It's not reflexive because little d is an element of A, but the ordered pair D comma D is not in curly R, i.e., there is no loop at vertex D, is there? So it fails. Even though we've got three of the loops, that's not enough. We would have to have all four of the loops, so it's not reflexive. All right. So now let's think about symmetry. Here's our definition of symmetry. If A is related to B, in other words, if we have an edge from A to B, we need to turn around and have an edge from B back to A. Whenever there's an edge from X to Y, we need an edge from Y back to X. Do we have that here, Sean?
We do from A to C, but not from D to B.
And that's all it takes is the existence, right? Because this is a for all statement. And the negation of a for all statement is there exists elements little a and little b in A, where A was related to B and B is not related to A, right? So even though we have a vertex, an edge from A to C and one back from C to A, that's not enough. Here we have an edge from D to B, but we don't have the symmetric twin going back from B to D. So no, it's not symmetric. Remember, the negation of an if-then statement is an and statement. The negation of P implies Q is that P happened and Q failed to follow. Remember that? So it's not symmetric because DB is an element of curly R, but B comma D is not an element of curly R, i.e., there is an edge. If you just want to talk about the graph, you can do that. There is an edge from D to B, but no edge from B back to D. So it's not symmetric. All right, good. Now let's check transitivity. It's transitive if we see two ordered pairs where the second coordinate of one of them is the same as the first coordinate of another one. That's when we have the hypothesis of transitivity satisfied. And when we have the hypothesis of transitivity satisfied, we're looking for an element that appears as a first coordinate and as a second coordinate. Then we put them in this order where that shared coordinate is in the inside. And we need to find the edge from the outside elements. So one from A back to C. So in the graph, the way that we can think about it is this. If we have an edge from, say, A to C, and then from C back to A, we need to be able to get from A directly to A, and we can do. Also, there's an edge from from C to A, and then from A back to C. So C to A to C, crossing over on the A, we do have C comma C. And those are the only two edges besides edges involving these reflexive pairs that we don't need to check because they never make transitivity fail. AA and BB and CC never make transitivity fail. We only have to check edges that go between two different vertices. In other words, we only have to check the ordered pairs that have different coordinates. So it turns out that yes, curly R is transitive. And how do we justify it? Well, we have A comma C is in curly R and C back to A is in curly R. So we're checking to cross over on the C. Does that imply that A comma A is in curly R? Yep, we've got A comma A. And then if we put these in the other order, CA is in curly R and AC is in curly R. So now we're using the same ordered pairs, but our crossover element is the A because it's the one that's in the middle. What is the ordered pair we're checking for here?
E to C.
C to C, right. And we've got that. And if you look at these ordered pairs, there aren't any other ordered pairs where the first coordinate, like A, appears as the second coordinate in another ordered pair except for the A and the C. It's just these two. So it is transitive, but it's not reflexive and it's not symmetric. How's the focus? Is the focus okay? All right. So have you worked through any of the problems in the worksheet, Sean?
I've gone through a couple, but I haven't completed it.
Well, I would recommend that you work on the problems in that worksheet
Mhm.
and then come to office hours if there are any of those that you can't work, or if you want to check your solutions to any of those.
All right.
Is there a particular problem from worksheet for chapter 8 that you have tried or that you looked at and didn't really know what to do with it? Because we could look at one of those now or, whatever you want to do.
Maybe number 8.
Take a look. Let me share my screen. Can you see that okay?
Mm-hmm.
So we're asked to find a binary relation a relation on A that's reflexive and is symmetric but not transitive. Okay?
Right.
And in fact, if you look at last night's video, there's a suggestion that you try to build each of the 8 possible different kinds of binary relations on A's. There are 8 different ways we can mix and match reflexive, symmetric, transitive, or not reflexive, not symmetric, not transitive. And it's good practice to try finding one of each. So let's see if we can do this. We want R, S, and not T. Okay. And A has the elements 1, 2, 3, and 4 in it. All right, so right off the bat, we know we want this to be this down a bit because folks so investing. So what elements for sure do we need to put into curly R? Let's think about reflexivity first. If we're going to build a reflexive relation, what do we need to have in curly R for sure?
1 to 1, 2 to 2, 3 to 3, and 4 to 4.
That's right. So we have to have those for reflexivity. If we stop right there, that binary relation is reflexive and it's symmetric because there aren't any ordered pairs where the two coordinates are different. So we've got the ordered pair that goes back the other way because it's the same, you know? And it's actually transitive because we don't have the hypothesis of transitivity satisfied. We don't have two different ordered pairs where one of the elements of A appears as the second coordinate in the first ordered pair and then appears as the first coordinate in the second ordered pair so we could cross over. So this actually is an equivalence relation, and each of these elements is living in its own private little equivalence class. But we are asked to find a relation that is reflexive and symmetric. Okay, we've got that, but we want it to be not transitive. So we need to add enough elements to satisfy the hypothesis of transitivity, but we want to make sure that the conclusion of transitivity fails. So let's just take a look at our definition of transitivity. We need to add elements where we have a crossover element of A. It's, like we're calling it B here, but we need a little a related to a little b, and then that same little b needs to be related to a little c, and then we want to make sure that a is not related to little c, right? We want the hypothesis and not the conclusion. So do you have any ideas of some ordered pairs that we could put into R that would make it not transitive?
2 to 4.
Okay, if we put 2 to 4 in there, right now it is still transitive because the only crossovers we could have would be with the ordered pair 2, 2 or with the ordered pair 4, 4, using 2 and 4 as the crossover element. And these elements, 2, 2, and 4, 4 of the binary relation, will not make transitivity go bad. So we're going to need another ordered pair. So it looks like you've set us up to try to cross over on the 4. So what's another element that we could throw in there?
4 to 1.
Sure. Good. So now we're crossing over on the 4. And what's the element that we would need to have that we don't have if we wanted it to be transitive?
3. I think it's 3.
I'm talking the elements. I'm not talking about the elements of A. You're
Uh,
right. You're right. I'm talking about the elements of curly R, the ordered pairs. Right now, we have these two ordered pairs, and they satisfy the hypothesis of transitivity. Right? We're
uh,
crossing over on the 4.
right.
So, so right now, this is not transitive. What's missing that's making it not transitive?
Um, from going to A to C.
Yeah. So A is 2, B is 4, and C is 1. So what's the missing ordered pair that we're not going to put in here?
2 to 1.
That's right. So, but hang on. Now we've added these ordered pairs, 2, 4, and 4, 1. And they have made symmetry go bad, haven't they? So now we need to add some more elements because we want this to be symmetric. It was symmetric before we added ordered pairs where the coordinates were different. But now that we have the coordinates different, we're going to need to add some more ordered pairs to get the symmetry to come back up. So what ordered pairs do you suggest that we add to repair the symmetry that we just lost by adding these two?
4 to 2.
Yep, we need 4 to 2. And what else do we need? What would be the symmetric twin of the ordered pair 4, comma 1?
1 to 4.
Yep. So curly R, so in our verification, curly R is reflexive, right? Because, X comma X is in curly R for each element X and A. Curly R is symmetric because 2, 4 and 4, 2 are in curly R, right? And 4, 1 and 1, 4 are in curly R, and we don't have to worry about these other elements. And then how would we explain why curly R is not transitive? What would we say to verify that?
Say 2 to 4 goes to, wait a minute, 2,
2, 2,
2 goes
4
to 4,
is an, or you can just say ordered pair 2, 4 is an
uh,
element of curly R. What else do we need to say?
and 4, 1 is element of curly R,
Nice.
but, 2 to 1 is not element of curly R.
Perfect. That's exactly right. Does it make sense?
Yeah, it makes sense. I just gotta like break it down like a little bit more
Yeah.
in my head.
Yeah, it's always about breaking it down in discrete math, isn't it?
Yep.
That's all we do is try to break stuff down. Good. Nice job. So I recommend that you watch the video from 12:9, and we talked about binary relations, and there's some suggested do laters. Okay. So
Okay.
between that and the worksheet, uh, you really do have to push a pencil, right? You're going to have to sit down and push a pencil or a pen or whatever you like to write with. Isaiah, do you have some questions? It's your turn.
Yeah, I mean, it's more just like review, going over, just making sure that I'm thinking properly on certain things. I wanted to go over some proof stuff.
Okay.
Uh, possibly.
Ooh,
We could do. What
I've
is
got
this?
one I want to talk to you about.
Yeah, of course.
All right. Proofs and counterexamples. This has been a while, so I'm really glad you asked.
Yeah, it's been a while since we went over like proof by contrapositive, counterexample, stuff
All
like
right, how
that.
about primes? Remember primes and composites?
Yeah. Yep.
All
I
right,
remember.
let's do one of those.
All right.
Okay. True or false? Prove if true, give a counterexample if false. Okay? Here's the statement. If P and Q are primes, then 2P plus Q is prime.
So
So if
what
we,
this is
yeah,
saying is essentially that assuming, like we assume that P and Q are prime,
right.
then then positive P plus Q is prime.
2p, no, it's not positive. It's a 2. 2p
But
plus q. All
if
right,
it,
so let's try, let's do some scrap. Let's try some different values for p and q and see if 2p plus q always turns out to be prime.
yeah,
All right, so what do you want to try for p and q?
we can start off with. I mean, there's no distinction between whether or not they have to be distinct, or there's no.
Yeah, yeah, that's right. Nobody said they have to be different.
So we can start off with just two, just to start.
Let them both be 2.
Uh-huh.
All right. So if P is 2 and Q is also 2, then what is 2P plus Q going
Four.
to equal?
Okay. It's essentially 4 plus 6, which equals 6. With the 6 is a composite number, so we got to change it up.
So we got a counterexample because 6 is equal to 2 times 3, and 1 is less than 2, and 1 is less than 3. We found
Yeah,
proper factors. So
yeah,
here's our counterexample.
yeah.
And that was a great catch that you realized nobody told us that P had to be different from Q.
It makes it a lot easier when you just say, "Hey, look, do they have to be distinct?" No. All right, boom. So then let's just start off like that.
So let's just see. Yeah, right. And so um, now, do you know how to write up the counterexample?
You would write the counterexamples technically, wouldn't it be just the negation? So you'd write it as there exists.
Yeah, we're going to prove the negation. So what is the negation? There
Counter,
exists,
there exists P and Q and elements of big P or
uh-huh.
primes that 2P plus Q is, or you can say composite because the negation or the opposite of a prime is a composite number.
It's usually composite if this is big enough, but there are other reasons why something might fail to be prime. Um, for example, uh, if this was like a minus sign, we could wind up getting a number that's negative or 0 or 1, and those wouldn't be prime either.
You're right.
Right, but because P and Q are both at least 2 and there's no negatives here, it's going to be
It,
composite, but I'll just write not
it's not
prime
prime because yeah, sorry, yeah.
because not
Okay.
prime might be not prime for other reasons. You
Yeah,
don't need to
you're
be
right.
sorry. You're doing fine.
You're
So
right.
here we consider, just remember the way we start a counterexample. It's an example proof, right? We're proving the
Mm-hmm.
negation. So just consider P equals 2 and Q equals 2. Now, what is it that we have to say about uh, P and Q? We have to first verify
As I
that they
said,
live in the right domain,
yeah.
right? So verify the domain. So what do P and Q have to be?
They have to be primes.
So what do we say to verify that these are prime?
This is where I forgot. I forgot what we say after
All
for
right, notice 2 is prime because it's only
because it's only
divisors.
divisor is one in itself.
That's right. It's only divisors. And we're talking positive divisors
Mhm.
are 1 and 2 itself. Good. Great. And then part 2 is to verify the property. And the property is that 2p plus q is not prime. So let's
Yeah.
talk about 2p. Tell your reader what you're looking at.
Yep.
So what is 2p plus q now? It's 2 times
Two from
2
two times two
is
plus
2
equals
is
6.
6. And so we want to show 6 isn't prime. So how do we do that?
Divided by 3.
Well, we have to give a factorization. Remember, uh,
Oh,
n is not prime if n equals a times b, where 1 is less than a and 1 is
mhm.
less than b, where a and b are integers.
Yeah.
So 6, note 6 is equal to 2 times 3, and both 1 is less than 2 and 1 is less than 3. So we've gotten 6 looking like a times b, where a and b are big enough. You know, it's no good if A is 1 because you could factor 5 into 1 times 5. That doesn't make,
Yeah, that
5
doesn't prove anything.
composite, right? You got to get those factors to be bigger than 1. Okay, great. But you know what? Just because, so check out that statement. If P and Q are primes, then 2P plus Q is prime. Well, what about this statement? True or false? Same instructions as example 2, okay? Here, I'm going to give a similar statement just to make a point. If P and Q are prime or primes, you can actually say it either way. You can say it singular or plural. It's a weird word that way. Then 2P plus Q is composite. Now, we found an example where it turned out that 2P plus Q is composite, but this statement is claiming that 2P plus Q is always going to wind up to be composite, right? Because this
Yeah,
is an if-then, which is a universally,
statement, yeah.
yeah. So what do you think? Do you think we're going to be able to find a counterexample to this, or do you think it's always going to turn out to be composite?
I would probably I'd say go over a couple of them. Like let's just like keep it pushing. Like let's
Yeah,
keep
let's
going.
keep looking
Let's
at some
keep
more
going.
scrap, right? Let's look at some more examples for P and Q. And then
So
what are we trying to figure out? What kind of 2P plus Q are we trying to find, maybe?
we're trying to find yeah, so we're trying to find if 2P plus Q is composite. So we can start I mean they don't have to be we can do three.
All right,
We
so
can
you
use
want to use
three.
3 and
We can
3?
use three, yeah, two threes.
All right, let's try it. So 2P plus Q is 2 times 3 plus 3, and that's 9. That's composite.
Composite. So
In
then
fact, do you realize that 2P plus Q is going to equal to 3P if P and Q are equal?
three. Yes. I did.
Right.
Okay, yes, that is true.
So it's
Mm.
always going to wind up to be composite if P and Q are the
They're both
same.
say the same. I
So
now that
maybe
you
we
say it,
should
that is
look at an
true.
example,
An
right?
example where they're different.
Yeah. So what do you want to
Um,
try?
let's do 3 and 5.
All right, let's try 3 and 5. So 2P plus Q is now 2 times 3 plus 5. What is that?
6 plus 5, which is 11, which is a prime number.
Ha ha ha. So
So we
sometimes 2P plus Q is composite, but sometimes it's prime. So neither one of these statements are true.
are universally like are universally
They're
true.
not negations of each other,
Yeah.
because if they were negations of each other, they would have the opposite truth value. They're actually both false statements.
So
Isn't that interesting that they're not negations of each other, even though it kind of looks like they are negations, but they're not?
yeah, it makes a lot of sense.
Because
Okay.
the negation of an if-then cannot be another if-then.
If then that's true. It has to be
All right,
negation of
so
it then is negation of it if then is an and, right?
the negation of an if-then is an and, right? The
Yeah.
negation of P implies Q is that P happened and Q failed to
And Q
follow.
failed.
So I'm going to say you write up
The
the
rest.
counter example for that one.
Oh, the counterexample for this.
Yeah, you can do that later. Okay.
Oh,
So do later.
okay.
But I mean, it's going to be very similar to what we did here, except this is going to turn out to be prime.
Yep.
So we'll talk about why it's prime instead of why it's composite. All right. So that's one class of problems. I just wanted to throw that out there because it might be one that you might miss when you're thinking about all the many things that we did. But
Yeah.
these were definitely in special homework. Anyway, so what about you were saying proof by contrapositive?
We could do proof by we could do proof by contra no, I want to do proof by counterexample. I would like I have a question. Is rationality like irrationality and the irrationality questions that we talked about on this exam, right? On our first exam or test two, it was more of a conceptual. Like, remember how in special homework, like I believe it was eight, mini homework special homework eight, you told us to like, okay, remember those steps? It was like you wrote out those steps. Okay, what is the contrapositive going to be? What is the counterexample? Write it
What's
down,
no,
write the
what's the
hypothesis.
contrapositive? It's what was the contrapositive? Because
Yeah,
you had to
excuse me.
write the contrapositive and you actually had to write the negation because
Negation. Yeah, it was like
proof by contradiction, you assume the negation and show that it leads to a contradiction. But
yes,
proof by contrapositive is you prove the contrapositive of the statement, which is like a direct proof of the contrapositive.
yes.
So
This I have a question about the final exam. Were that irrationality question that we didn't get the full brunt of on test two? Is that gonna be a question that
no, I'm not. I'm not going to do that to you.
okay, okay, okay. All right, so then we go over counter exam. Sorry, contrapositive, not count. Wait, it was contrapositive. Proof by no, we don't need to go over contradiction because I remember contradiction. We go over contrapositive, excuse me.
Water. So a lot of times you can use either proof method if you need an indirect proof. So let's look at some examples. In fact, if you go back and look at the notes, and this would have been section 4.7 class notes, where we talked about proof by contrapositive and proof by contradiction. In fact, let's do that. Let's go back and look at those class notes. I just want to show you what I did for you then, which might not have really registered with you at the time. It's kind of hard to realize what all went into things until you go back and realize, oh, there was a method to this madness. Okay, so on day 14, it was indirect proofs. Okay,
Mm-hmm.
and here's our little chart on what to assume if we're trying to prove if P then Q. Like we never use an indirect proof for proving an existent statement. We only use indirect proofs when we're proving a for all statement, an if then statement. Okay.
Mm-hmm.
So direct proof is the proof that we're really very comfortable with, which is kind of beautiful news when you think about it, how much you've learned. You just assume P and you try to prove Q, right?
Mm-hmm.
Now, proof by contrapositive is a direct proof of the contraposition. You assume not Q, and we wish to show not P. So in some sense, it is a direct proof of an if-then. It's just we're proving the contrapositive formulation of the if-then, okay?
Mm-hmm.
Proof by contradiction is a whole different ballgame. We
That's
assume the negation
negation.
and then find a contradiction.
And that was like a mathematical contradiction to where this pot like y can't be rational or y is right. Like I remember. Yeah.
Right, right. Why can't be both?
Y can't be both, yeah.
So this first example, we actually proved it two different ways. We proved it by contrapositive and we turned around and also proved it by contradiction. You might not have really realized that at the time, but I wanted to take a simple statement. This is a super simple statement. If n squared is even, of course, n is an integer, then n is even. Super simple statement, but you can't prove it directly because if you try to prove it directly, we're assuming n squared is even. And then remember, we got the square root of 2,
Mhm.
and that was no good. Like
Yeah.
that doesn't help us prove it that n is even because the square
Yeah.
root of 2 is not involved in the definition of even, right?
Yep.
So we wrote the contrapositive. If n is not even, then n squared is not even. In other words, if n is odd, then n squared is
Mhm.
odd. And we proved it.
That's an easy proof.
It's so easy, right? And
Yeah.
then here's the steps for proof by contradiction. We went back and attacked that same lemma and then proved it by contradiction, where we assume P, so we assume n squared is even and not Q, that n is odd. We wind up running with the fact that n is odd, prove that n squared is odd, but that contradicted our assumption that n squared is even. So
Mhm.
a lot of times you can prove it either way.
I hear you.
And then my favorite kind of proof by contradiction or contrapositive is to prove
Divide.
a does not divide statement. Because if you try to prove it directly, the hypothesis that c squared does not divide a squared plus ab doesn't help us at all. We can't get any equations from c squared doesn't divide. But if we write the contrapositive, then this or statement, since we're negating an or, becomes an and we wind up having lots of hypotheses that c divides a and c divides b. And then we get that c squared divides a squared plus b squared fairly easily using definition of divides. And then here's stuff with rationals and irrationals. And I'm not going to give you a question on rationals and irrationals. I'm willing to say that right now.
All right, good. Thank you. All right.
But let's work on a proof by contrapositive or contradiction that looks like, well, let's do one of my favorites. Proof. For all A, B, and C in Z, if A cubed does not divide B squared C, then A does not divide C or B does not divide C.
It does not divide zero. Okay.
So, how do you want to attack it? Contrapositive or contradiction? We can do both.
Contrapositive.
Okay.
Contrapositive for sure.
Proof by contrapositive. I'm in agreement because I like proof by contrapositive because I don't have to worry about what my contradiction is going to be.
Mm-hmm.
Sometimes proof by contradiction is really the only way to attack a problem. Problems involving one rational and one irrational really can only be proven using contradiction. But anything you can prove by contraposition, you can prove by contradiction. The converse of that's not true. Just because you can prove something by contradiction, it doesn't necessarily mean you're going to be able to attack it by proving by contrapositive. But we can try contrapositive. So let's write the contrapositive first. Let's write it right here. Still for all A, B, and C in Z, because it's still an if then, right? So
It's
what's our if part? What's our
be
hypothesis?
if not Q, then not P.
Mm-hmm.
So it'd be if A divides C and B. Oh, no, sorry. If A divides A and C. No, if A divides C and B divides C, excuse me.
Yeah, it's not that A divides both. It's A divides C and B divides C.
And B
Then,
divides C. Then A cubed divides B squared C.
good.
Yeah.
So we're going to assume,
So we assume
well, that A, B, and C are integers first. Okay, we just get that out of the way.
A and C are elements of Z. And then also, no, that's proof money too.
What else should we
Mhm.
assume?
We assume that A divides B and B divides C.
Oh, you're right. I've got a typo.
Where?
Good job, man. Then A does not divide B, or B does not divide C. I want a B here.
Oh, I don't even my brain just automatically put that in. I didn't even like I
Well, my
just said it.
brain should have.
I just said
So,
it. I didn't even
so we'll assume A does divide B and
and
B
B divide.
does divide C.
That's extra credit.
Sure, you can email me for
Yes,
extra
sir.
credit. Nice job.
All right, baby.
No, thank you, because
Make sure I email right after this.
we could probably prove them both, but I like this problem better. Okay. Yeah. All right. So what do we wish to show?
We wish to show that, excuse me, I'm still writing. We should show that a cubed divides b squared. See.
All right. So we're all set up. We know what we've got and we know what we wish. So what do we do now?
We use wait, first we go, let me think. I want to use my proof money,
Yeah, we need some proof money.
but first we need proof money, but also we need to go by the definition of divides as well.
Exactly. You heard the voice. Use the definition.
Yeah, use the definition.
So let's use the definition, which is divides.
Yep.
So what do we have?
You say by the
Since
definition.
A divides B, what do we know?
Since A divides B, we know that A and B are elements of Z.
Well, listen, 7 and 5 are elements of Z, but 7 doesn't divide 5. We're going to use, since A divides B, we need to use the definition of divides. What kind of equation do we get?
Oh yeah,
All right.
we get a B equals A times an integer or whatever you
Okay.
use K. Yeah.
For K is in Z. Great. So we've got some proof money, but we're going to get more proof money than just that. And that's great. Part one and part two of the definition of divides. All right. So what else are we going to get from our hypothesis?
K what are we gonna get from our since
We get some more
yeah, we got
hypothesis.
some more hypothesis money, so we could say that since B divides C,
Uh-huh.
C equals B times an integer, whatever you want to use, whatever you can use, we can use
All right.
whatever.
Let's say M, where M is in Z.
You
Okay.
know,
Let's look at our wish. Let's think about the kind of equation we need to get so that we can get our wish satisfied.
so let's look at a wish.
Yeah, let's unwind our wish a little bit so we know what we're shooting for.
So our wish actually looks like uh we wish to show that B squared C equals a a cubed times an integer.
N, okay?
And
You
yep.
just have to think up some letters where N is in Z. All right, so that's our wish. That's our dreamy wish. We can't start with it, but we can try to get there. So what quantity should we actually be looking at to try to get our wish to happen?
We should what where should we
Well,
look
yeah,
at?
well, we've got B squared C is one of the quantities involved in our wish. A cubed N is one of the quantities in our wish. Like our wish is an equation involving two quantities, and we want to show these are equal.
Yeah,
So we need to decide which of these two quantities we're going to attack.
we're gonna attack I mean a cubed n.
Oh, really? So if we attack A cubed N, then we would need to be able to plug something in for A. And
Oh, we don't have enough
see
money
what I'm
plugging for A.
saying? So
So
look at your
yeah,
money, right?
yeah, we need to use our money and we don't have A money, so we need to use B. We need to use our B and C money.
Okay, so now we're going to tell the reader, hey, check this out, observe. We're going to look at B squared C. We're going to look at that quantity. So what is B squared C equal to?
B squared C is equal to AK squared.
AK quantity squared. Yeah, because the A is going to
Mhm.
get squared and the K is going to get squared.
Yep.
And then what is C?
And then C is gonna be BM. Yes.
Good. Now, it's nice that we have our wish right in front of our very eyes because right now, what do we got? We've got B squared C equals A squared times K squared
B squared
times B
B
times M.
M.
But we need A cubed. We only have A squared.
Well, we could substitute again.
Yes. What can we
We have
substitute in
unlimited
for
money.
again?
We have unlimited money. So B equals AK, so we have another AK.
That's right.
Yeah, I remember this. I studied hard for this test. I studied hard for this one.
That's good. So now we've got three copies of A, right? We've
Yep.
got A squared times another A is A cubed. And then what do we have left over? What's the other factor going to be?
Um, A, wait, no, we took out the A. We're gone. It's K cubed. It's K cubed and M.
Times m. Great. And that's going to be
And you
our
can,
integer n, isn't it?
yes, it is.
So we just have to now, so we've just satisfied part one of the definition of divides. We got that b squared c equals a cubed times something,
Yep.
but we got to satisfy part two of the definition. We got to show that that
Yep.
something is an
Show
integer.
that integer, and we also have to say something smart about products.
Yes. And use closure of the integers under products. So tell your reader, hey, remember K, because we haven't burned the money yet that K is in Z and M is in
M
Z.
and
We
Z.
burned this money a couple times, right? But
Yeah.
we haven't, so but see now when we realize, oh, we got to use this.
So we can't we just say, so see, we say since or notice
Uh-huh.
um n equals K cubed um times M is an element of Z. Well, actually, we could put as an element of Z
Yeah, is an integer
because
or is an element,
and
or you could put element of Z
element of Z
because why?
because K is an element of Z.
Yes. And what else?
And well, we could say wait, where's it? All
We
right,
still haven't used it
we
yet.
haven't used this money yet.
Well, you just
M
used K as in Z, but now you want to burn M as in Z.
and oh yeah, we have to burn both of them because M is in included in N. So technically, we got to say that M is an element of Z too because it's
Uh-huh.
included.
And what do we say to show that K,
And products of integers are integers. Excuse me.
perfect, nicely done. So in fact, B squared C, I don't like the way that looks, is equal to A cubed N. So B squared C equals A cubed N, where N is in Z, because that's what we just proved. Part one, and this is part two
Oh yeah, I
of,
remember this.
of the definition of divides. Yep, just being methodical. And it's really nice that you realize proof money, it's great to burn it, Where, I think this where needs an E there. So A cubed divides B squared C by what definition?
By definition of device.
Nicely done. And there you have it.
Yeah, I remember. Yeah, I tried to warm up on this, but this should be. I
You
should
want to
be.
do later?
Yes, please.
For all A, B, and C in Z, if A to the fourth does not divide B squared plus C squared, then A does not divide B or B does not divide C.
You put an or right there.
Yeah, because when we make the negation, that becomes the and.
And
And we need both of those to get negated with an and in between, because we're going to need to know that, and this is not right. This should be A squared.
okay. It would it hypothetically. I mean, we probably won't see this, but in hypothetically, if we did have like to the fourth, would that
It
matter?
wouldn't be true. We wouldn't have
Okay.
enough. No, we'd have to have like B to the fourth or B squared, C squared plus,
Mm,
C to the fourth. You need four copies of A in each of these terms, but we're only going to get two copies of A.
mm. All right. Yeah.
Okay. John, do you have another question?
Not as of right now, no.
Okay. Well, I totally encourage you to work on those worksheets. Look at all the office hour videos because I gave lots of do laters all week long, and
Mm.
we'll continue with this having office hours. I think the 7 o'clock hour is a little nicer for me. I'm kind of running a fever. I didn't want to stay up real late tonight, but your exam is at the printers, and it's 14 questions, 200 points. And this is really good coverage that we've had tonight, Isaiah. You should definitely do your colleagues a favor and come to office hours tomorrow night and continue along the lines of questioning that you are pursuing because uh, I think that this a particular office hour should be very helpful as people are trying just to remember stuff because we've covered a lot of material this semester.
Yeah,
You definitely are doing well. It's coming back to you. So sit down and do this do later, right?
of course.
And then check out some of you don't have to watch the videos. The notes are up, and with the do laters from earlier in the week, you can check those out and just attack the do laters and watch the video if you need to.
I'll be here tomorrow. I think I want to talk about some intersects tomorrow. Intersections
Hey,
and
hey, hey. We want to talk about some of these interval notation things.
yeah.
Did you? Okay, so there is, did you know? Let me just show you what's going on. I really do try to make materials readily available. So in the YouTube, if you go to the office hours, to the playlist that's office, I'm seeing more than you're going to see, okay? Because I've
Hmm.
got, look at all these playlists I've got. I've got so many, most of them are private. But if you go I don't want that to start talking. But if you look at like the office hour last night, if you just look at it in the description. So welcome to office hours. Yeah, we don't need to hear me again. One of me is more than enough. But if you look at the description, it tells what we covered.
Okay, I see what you did there.
I did that with all of these office hours,
Hmm.
where you can look at the description. So welcome to So functions, images, and inverse images onto one-to-one prop. But we definitely covered what you're talking about. Um, yeah, the intersection operator,
Yeah.
indexed intersections involving interval notation. So that's December 7th.
Okay.
So
Okay.
the
I covered
notes
it
are
then.
up, so
Yeah.
you can attack the notes or watch the video. Uh, we did have a sort of a lengthy discussion about that was a really long office hour, I think.
Yeah, I think I missed that one.
It's okay. That's that there's honestly an advantage to having online classes if it's live. Like I've taught this class online before. And the nice thing about that is that all the lectures are recorded, all the notes are posted just like they're posted, but you get the advantage of the lectures recorded. So I think we got a lot of good stuff out of COVID. One of it is this idea of having video recordings.
Of course. Yeah, you're right.
Isaiah, thank you for coming. Sean, thank you so much for coming and asking questions. And what is 7 o'clock a good time for you gentlemen?
Yeah, 7 o'clock is great tomorrow.
All right, Sean,
I got a final at well, it ends around 7, so I might be a little late to that.
that's fine. You don't have to come on time. You can drop in or out, or if if there's something in particular, Sean,
Hmm.
uh, you could email me and say, "Hey, Dr. Good, I'm not going to make it to office hours, but could you talk about, and then tell me a particular problem from either a homework test, worksheet, or quiz." Then I can make sure that I talk about it. But if you're going to make it, even if you're late, I'm happy to, you know, try to help however I can.
All right, thank you.
You're welcome.
All right.
All right, gentlemen, I'm going to call it a night and process this recording and get these notes up.
All right, yes, thank you so much,
All right, have
Professor.
a good night.
Have a
Yes,
good
have a
night.
good night.